Yeah, so it's a good idea to try to figure out what is that what's missing and why. Uh, so you didn't get the right answer, so we gotta find out why. So then you have missed something. So that would be good to, rather than just solving the problem, try to figure out what that was overlooked. So okay, so f of x is, does it really matter what that function is? You know, you do one, you know them all. So 1 over x or anything else. How about 2 over x plus 1? Okay, why not? It's the same thing. And the difference quotient. Okay, so difference quotient, and so you were given two values. You're given two values of x. That's all. Right? So we'll say over. So those two values, what they do, they form an interval, a segment. And so say it could be x equals say 1 and x equals 2. Okay, so which means we're talking about the interval 1, 2, and we are looking at what has happened, not everything what has happened, but what is the difference between the value of the function at the beginning and at the end relative to the change of x. So that's the change of x right away, 2 minus 1. And then change of y, that's what you need to find, and then you just divide it. So what the, can you try to?
I did the whole
Yeah.
f of x plus h
Yeah.
minus f of x
Yeah.
over top of h.
Yeah.
And I just couldn't get the right answer. I tried it 5 times.
Anybody has had the problem with this one? No. So you probably, so remember, first of all, if it is frequently, this is easier, easier formula for difference quotient when there are two specific values given to you. Okay, so I would rather put say a here like this. Okay, so they are equivalent. Right, so the transition is simply h is equal to x minus a, and if you make that transition back and forth, you get the same formula. So it's just the way it's just a matter of bookkeeping. So a plus h, and this is h. Okay, so that's all. You can certainly go to the left as well. But this one is easier if you were given two specific values of x, as we have here. Then you just plug them in. So you can be specific. You don't have to. Sometimes if there is no limit concern involved here, so if we are talking about literally about the average rate of change, the average rate of change, the average velocity, you don't get to that next step of taking the limit, then you don't have to have anything more than this, and you just say b is equal to 2, a is equal to 1. It is possible that, I mean, something that happens in my experience is as simple as that just the order of numbers. It probably was wrong, and you may be getting you're getting the negative number of what you were supposed to. So they have to follow b, then a, same as the numerator and denominator. Or a followed by b, doesn't matter, but the order should be the same in the numerator and denominator. So in this particular case, it will be 2 over b plus 1 minus 2 over a plus 1 over b minus a, okay, in that order, as you can see. And then you just simplify. In our particular case, we have 2 over 2 plus 1 minus 2 over 1 plus 1, 2 minus 1. And, well, that's all there is, 2/3 minus 2/2. Okay, so negative 1/3, is it? Yeah. Okay, so computers are unforgiving, so it doesn't matter how small a mistake you've made, they won't it won't give you partial credit or anything like that. So if you just your denominator was 1 minus 2, the answer is wrong, and that's the end of it. Okay, so it's hard to get to. It's good if you would had written up your solution, and then we could look at it and see what's
Yeah, I don't have a clue where that'd be.
right. And then it is important. It might be important. Might be something unimportant or minor, or might be something important that you actually overlooked, and that it would be nice to get it now rather than later. Okay. So this is like I said, it's online homework. That's what happens. Okay, so this is the last topic. We are producing now. So it's like two stages. The one that we just discussed is the first stage, difference quotient, 2 points on the graph, and we're looking at these 2 points, and we're looking at rise over the run. Okay, numerator over the denominator. Stage number 1. Stage number 2 is to look at what we have done before, to look at the limit. So b goes towards a, or same thing as h goes towards 0. Okay, and then the end result will be a number, well, it is a number in either case, but in this particular, under this idea, you will have the behavior of the function, instantaneous behavior of the function. So that will produce the derivative. Okay, so and then the third step, we are climbing. It's certainly it's not getting any easier. We do that at every single point. Okay, so as you can see at those, that's what I did yesterday. These are the yeah. So remember how I did it. So these are the tangent lines. I drew these tangent lines here, and then I dragged them there to just to keep record, and then I look at the slopes. And those slopes combined produce the function, which is the function of the derivative. Okay, so this is the derivative of this function. Okay, so whole function, continuous curve, are likely to produce something that is also looks like a continuous curve, and that is as the derivative. So that's what the geometric meaning of it. A bunch of tangent lines, and let's face it, it's really quite. It is a complicated concept, and just imagine. So what we're talking about, we have a curve, and then what we're talking about is look at every single point, and at every single point there's a tangent line. So I can only do a few, but you can imagine that every single point, it's like hairs or something like that, are attached to every single point of the curve. We take them together, and then we want to make sense of it. Okay, so the directions are tangent, so all these tangent lines, and the best you can tell is find something from real life. It is you're driving on the road, and you just watch the your headlights. So headlights go at the tangent whenever you curve. Either if you see your headlights are lighting up the road, you know that your tangent, it coincides with the curve itself, with the road itself. Once you see the trees, you know that you're turning. Okay, and in that way you know which way you're turning. And then you can sort of detect which way these lines turning. Okay, so in this particular case, so we start down, and then it's turning counterclockwise, right? You see how we're starting down and then turning like this, and then this is counterclockwise. And here you turn clockwise and counterclockwise again. So that is a behavior of a function. So every slopes taken together form the derivative. That's exactly what you see right here. Slopes recorded as values of the function. Okay, so we throw out those lines. We throw them out. And we record only the slopes. These are the slopes, and that's my new function. So it's not easy, and the two skills that you need to initially is doing something like that. So evaluating, figuring out what the graph of the function will look like, and second one is computational. Computational, so you have a formula for the function, and you find the formula for the derivative. Okay, so that's the topic we are we're right now dealing with. So, well, computing derivatives. Derivatives are to begin with, are limits. So all the things that we have learned about limits will help us to produce rules of differentiation that are similar to rules of limits. So every rule of differentiation will have a rule of, every rule of limit will have a corresponding rule of differentiation. But we'll start with something. Well, let's start with simple functions. That's the way to go. Start with functions, and so that you will always have like at least a very short list of functions that you know derivatives of. And the simplest function is constant. So the constant function well, you can certainly guess, and that's a good idea if you can do it both computationally and graphically. Do both, because that's the way really to connect the dots and to remember things. So that's what the graph looks like, right? X and Y. Okay, so you just what the plan that I had. It looks really simple for this curve. What do the tangent line look like? These are the tangent line. There is no doubt what those lines are. The tangent lines are the curve, the line itself. Okay. Okay, so the slopes are then, what are the slopes? 0. Okay, so that's the answer. So if f is constant, either throughout its domain, or there's a part of the curve of the function, if it is piecewise defined, that is constant, then its derivative is 0. Okay, so this is what I meant. If you have a function like that, it will be non-differentiable on the endpoints, but at least on the endpoints, you know that at every point the derivative is 0. As you can see, for a function that has 0 derivative, to go anywhere it has to jump and be discontinuous. But at the very least, it is if you have a flat horizontal piece of the graph, it means that the derivative is equal to 0. For completeness sake, so let's just look at so f and do it computationally. Say f of x is equal to c for all x. Okay, so f prime of say x is limit h goes to 0 f of x plus h minus f of x over h. So that difference quotient we have been writing, and we'll be writing a little bit for a little bit more. So I plug in c everywhere. So what's the numerator?
C plus h.
Yeah, so f of f no. C is the value, not the, it's not the input, it's the output.
C plus h minus c over h.
No. This is the, it doesn't matter what x is. Is it x? Well, what's the second term? What's the second term?
C.
C. Okay, what's the first term? It doesn't matter what x is. That's the constant function. Doesn't matter what x is. You have x or x plus h. The value is the same. C. Right?
Yeah, because it's not changing in height.
It's not changing, right? So the value disappears, as you can see, just as the formula states. It just happens to be independent of x. So it doesn't matter what you plug in. The output is the same, and then you have your limit of 0 over h. And this is one of those cases, of rare cases, that you don't have to worry about limits, because, well, it is 0. limit of 0 is equal to 0. Okay, even though h goes to 0, it appears that you're like dividing by 0, but really not, because h remains positive in the limit. And then so you end up with limit of 0, which is 0. Okay, so that's the computation right there. Okay, so that's example 1, or the simplest function. What's the second simplest function?
A linear function.
A linear. Okay, so let's do linear. Number 2, f is linear, such as f of x is equal to mx plus b. M is the slope, b is the y-intercept. Okay, x is not did not disappear in the right hand side, so it does depend on x. Once again, I'll start just like with this one. I'll start with the picture. Y equal mx plus b. Okay, so what are the tangent lines?
It is a tangent line.
Well, once again, the picture is pretty much the same. And what are their slopes? If it is the slope of the tangent line is the line itself, so the slopes of the tangent line are the slope of the line. So what is it? M. Okay, so that's the answer. Let's do computationally, arrive to the same answer. So we have then f prime of x is equal to limit f of x plus h minus f of x over h. Okay. I substitute specific function, so it will be m x plus h in parentheses. Whenever in doubt, put parentheses in. Okay, I'll put the brackets here to separate the two terms in the numerator. Okay.
H over H.
Kind of. One step at a time. B will disappear. Okay, so what I'm left with is m, and then let me open up the rest. Mx plus mh minus mx. So first of all, the free term, the term without h, disappears every time. Okay, so that's b is gone in the last line. In this line, mx disappears, right? So I'm left with mh over h, right? So this part is gone. So it suddenly becomes independent. You already look at the expression, and there is no x present, as expected. And then we are pretty much done, because it's m, a constant, once again, constant limit is equal to m. Okay? So you can imagine that, we progressed from a constant function to linear function. The next step is quadratic function. You probably can imagine what's going to happen. Not by far more complicated. If you know that it's going to work out, you probably can finish the job. But let's do it once for one of the simpler functions. Say simpler quadratic function. Say so f of x is equal to, say, simply x squared. We already did it at one point, but now let's do the whole thing at once. Okay, so if you look at the picture, it is not telling us a lot. Y equal x squared. The slopes do vary. Okay, can you say anything about the slopes? Anything? How they're changing?
Goes from negative to positive.
From negative to positive through 0, right? So indeed. So, well, it looks from positive to negative, maybe like this, right? So from negative to positive, from left to right, from negative to positive through 0. And okay, so that's possible. That's what it's going to look like. And indeed, the rule is fairly simple for polynomials. Degree always goes down by 1. So that's we already saw it. the derivative of the linear function is constant. The derivative of the quadratic function is linear. The derivative of a cubic function will be quadratic, and so on backwards. Every time the power goes down by 1. Well, let's confirm that, at least for this example. So I have f prime of x is equal to f of x plus h minus f of x over h. And so I'll have a limit x plus h squared minus x squared over 2 over h. H goes to 0. Okay, all you have to do is to open up the parentheses and then just look things falling into places. If you do it right, things will fall into places. So you just expand the expression in the numerator, and you have x squared plus 2xh plus h squared minus x squared, right? So almost exactly the same thing happens every time, and that is the terms without h disappear. Okay, and secondly, once they are gone, what you do next is you divide by h. So this is the two steps. Number one, terms without h cancel in the numerator, and number two, we can divide by h. Divide numerator and denominator by h. Okay, so which also leads to cancellation. Whatever the meaning of that term is, it is a very broad term, and so you shouldn't force yourself. Sometimes you know what the supposed to happen, and you push it too hard, and then you use the word cancellation very liberally. Here there are two cancellations, but they happen by very specific algebraic operations. The first one we already had. It is simply subtraction or addition. So you just one minus the other equal terms. They are gone. So it's a cancellation, but it comes as a result of simply subtraction of two terms. The next one is again cancellation. So this is where we are. And so it's again cancellation, but again it's carried out with very specific algebraic operation. That operation is division. So we're going to be dividing. Let's stretch it out a little bit, and so I'll factor h out first. So I'll have h 2x plus h over h. And then now I do divide. So there's no magic here. The things that are just happening, and this two-step plan will work out every time you do computation of the derivative from the definition. Okay, and so now we have the end result of these two steps is no 0 over 0 anymore. So that division by h, the h was the problem in the denominator. Now we have divided by h. And it's gone, and we have a continuous function. Hopefully. Okay, so carefully look what h is. Continuous, but with respect to, that's important. That's another place easy to make a mistake. Which one is there are two letters, and you might mistake one for the other. H goes to 0, so it is the one that to be replaced with 0. So the answer is 2x. 2h. 2x. Okay, so this is the kind of I suppose, 4-step procedure process. So eliminate terms in the numerator that do not contain h. Then divide by h. Observe that you don't have division by 0 over 0 anymore. And then the function should be continuous, and then you just evaluate the limit by substitution. Okay. So once again we're confirming the picture at the top, right? So it is indeed a function that goes from negative to positive through 0, and that in general is how it works. However, I could give you a better formula. Derivative, and that's another notation. Ax squared plus bx plus c. If I don't want to use I don't want to have a name for the function, I want just a formula such as this. So my function ax squared plus bx plus c, no name, just a function with three unspecified constant numbers a, b, c. I differentiate with respect to x, and the answer is 2ax plus b. Okay, so that certainly saves time, and you definitely can see that what's on the left inside the parentheses is any and every quadratic function, and then on right we have produced a linear function. So any quadratic on left, and it will produce a linear function on right. Okay, so that will work every time. If we go cubic, the result will be quadratic. The why it happens, you probably can observe at what point. This is where did it happen? Yeah, the square. You see where the square has disappeared, right? Very first step, we canceled x squared, and that makes what's left 1 degree lower, right? So with the highest degree will always cancel, because that's exactly the term that does not contain h. It will always cancel, and that will bring the degree down by 1 every time you do polynomials. Okay, so these are the basic, the two basic functions. Then polynomials work out pretty easily. But let's see. So we need more rules of the of differentiation, and they correspond to limits, to rules of limits. So let's just say, so we have a function, so y equal f of x, and they will have y equal g of x. We have two functions, and we put them together, we have y equal f of x plus g of x. So so it depends how comfortable you are with the rules of limits to begin with. Then you will see how comfortable you are with the rules of differentiation. It is about algebra functions. Old functions produce new functions, and we just see what that algebraic operation does to limits to begin with, and now what does it do to derivatives. Okay, so and the rule is, well, let's see. It's really uncomplicated. So we have the derivative of f. So this is a new function. Let's call it h. And my interest now is what is the derivative of what is h prime in terms of f prime g prime. Okay, so we know the derivatives of the two functions. It is like we already have two functions with known derivatives that we just considered, and we create a new function. And we don't want to do all this work. It's quite a lot of work every time from scratch using the definition. We want to use the information that we already have. So we assume that these two things are known, and then we create a new function that is unknown and its derivative is unknown. But since the two functions are known, their derivatives are also known, and all I will have to do is just to combine these two derivatives to produce a new one. Okay, so the idea, probably you can guess the answer. What is the meaning of two functions? Could be, let's think about x is time, and x is time, and say f or g, y being both y and g is the location. How do you have two functions? Well, two different persons working in different directions. So this is f and this is g. Okay, then when you add them together, the distance will be f plus g. Okay, and then so that's to begin with, and now what we're talking about is about the speeds. So one person walks that way at some speed, I don't know, 10 miles an hour, okay, 5 miles an hour. And the other one is running 10 miles an hour in the opposite direction. Okay, so you know what's going to happen together. You add, right? What's the speed of the how fast they're getting apart. How fast the distance between them is changing. 15. So it's 5 plus 10. It is 15. So the distance between them is, so there's some kind of a initial point of measurement, okay, where they started. Okay, so G measures the distance to that point, and F independently measures the distance to that point too, and they are working in the opposite direction. So then they know they are each speeds once again working in the opposite directions. And now maybe an observer does not actually see that red point in the middle. It sees how they walking apart, how far they are from each other, and then that is the person who would be just by measuring the distance, we would come up with 15 miles per hour. But really, those two persons, if they communicate and they know each other's speed, could just figure it out by simple addition. And so 10 plus 5. Okay. And then you can imagine that this thing is really fully applicable, this idea of addition, fully applicable to the possibility if both of them are not walking at a constant speed, but rather vary the speed. You can still keep adding the velocity, because that's how far at every moment of time they're being pulled apart. Okay, so that's an explanation. Hopefully, is realistic enough to understand why this the result is the derivative of the sum is equal to the sum of the derivatives, which is what this is. So these are what I'm talking about. This is f prime and this is g prime. Okay, so and this is h prime. Okay, so when both of them are constant, that certainly is there is no doubt about what's happening. So when the speeds are constant, when they're not, it's slightly less obvious. But think about it: you're measuring the speed at one moment at a time anyway. So it doesn't really matter what the distance is. It's how fast you're moving. So if you have two readings, two speedometer here and there, all you have to do is just do they change? No, as long as the reading is taken simultaneously, right? You add these. So suppose these are actually not two persons but two cars. You have two readings, and they each of the two persons calling you and telling you what that current speed is. At every moment of time, and you just write down, and you have your table of values, and you just add together the one for F and the one for G. So anyway, if we are to look at the actual limits, you can say, so h of x plus h. Oops, I guess I was not using the good letters here. I already have h taken, so let me. How about p? So that function is p. Okay, so that's p. Okay, so if I'm looking at p prime of x, it will be the limit of p of x plus h minus p of x, pp of x, p of x over h. Okay, but then I'll substitute what p is, f plus g, so it will be f of x plus h plus g of x plus h minus f of x plus g of x. So you see where what I'm driving at here? What do I do with that? What should I do with that expression?
Could you clean up the first part of it in the math bracket, in the brackets?
Yes, in the first, we'll do what with it?
Well, we got to get rid of x, don't we?
No, what we need to get rid of is h ultimately, but really when this is an abstract computation, so there is no specific function for us to take advantage of, and some algebraic properties of trigonometric properties that allows us to get rid of the of the h in the denominator. The plan is this is the plan, is to express the derivative of p, which is the limit of this, in terms of the derivative of f and g. And if I just write them down, this is what we want to arrive at: f of x plus h minus f of x over h. That is the limit of this is the derivative of f, right? If h goes to 0. On the other hand, g of x plus h minus g of x over h. This one, under the same limit, goes to g prime of x. Okay? So this is where we want to end up. We already have a conjecture about what the answer is. The answer should be the derivative of the sum, or sum of the derivatives rather. So the idea then is how to get from point A to point B. We know what we want to prove. We just need to get from that line at the top to the next line. How do I get there? You see it? Compare the terms. Look at the numerators and compare the terms. Compare the terms at the top and at the bottom. What do you see?
Everything's being divided by h.
Right. Okay. So that is certainly is the same. That is the same. Okay. What else is the same? Well, let's go term by term. F of x plus h, we have it. Okay. G of x plus h, we also have it. And then f of x, right here with a negative sign. And one more g of x is also here, also with a negative sign. So the terms match.
Combining like terms.
Yeah, that's right. What we do, we take what we have in the brackets, we get rid of the brackets and combine the similar terms. Okay, so it will be simply f of x plus h minus f of x. That's one combination. And the second one, g of x plus h minus g of x. Still by divided by h. So I just rearrange the terms, and then what's left is just to split it, right? So I take this expression and just split it like this. So that is, this is one, and this is the other, right? So we started with the difference quotient of p, our sum function, and then by rearranging terms we arrived to, so once again this is the difference quotient of p, and these are difference quotient of f, and this is difference quotient of g. And then all it takes, just the last step, is take the limit. So let me just state it. The conclusion, called the sum rule. The derivative of the sum is the sum of the derivatives there's a little bit of a condition that has to be verified before you apply the theorem. So provided the functions are differentiable. Because if two functions are not differentiable, then we cannot speak of the limits. That computation that we just carried out would fall apart at their last stage. But otherwise, if you have two differentiable functions, then you just put them together, and you don't have to compute the new derivative of that new function. You just say, well, there we go. They just add the two derivatives. Right now, well, as an example, I guess a very simple example, I will say x squared plus 3x minus 1. If I am to compute the derivative of this function, then I could actually use the sum rule of derivatives, because I have two similar functions here, x squared, and this one is quadratic, and the other one is linear. Okay, so we know what's the derivative of the first function. What? No, two of the first one is 2x, and of the second one is 3. Okay, so that's all it takes. You take functions when there's addition involved. You can break it into pieces and just evaluate the derivative of every piece, one at a time. So that's the sum rule. And what am I looking at here? And then there are three more rules. Oh, yeah, three more rules of differentiation. And the next one is the constant, not of differentiation, but of the of limits. And now every one of them will have a counterpart. Okay, so the next counterpart is the constant multiple rule. This time we have only one function. So, and then we'll multiply it by something. So you have y equal f of x, and then you have a new function, say p of x is equal to c is a real number, and c times f of x. It's a new function, and you once again you can figure out what the answer is, either going through computations or like we just did, or once again through interpretation of the of our derivatives as speeds or velocities. And so what happened here is so if x is time and y location, so multiplying y by c, it's what is it? It's like all the distances have become, let's say, 2 by y. What happens if you multiply all the locations by 2? It means that the distance is kind of a shrunk, I suppose. Okay, so it means that, or you say that I think it's better to put it as if you cover twice the distance, right? So if y is the location, x is time, okay, and then with the same setup, but now you multiply your location by 2 every time, which means that you cover twice the distance, right? Well, how do you cover twice the distance? What should happen to your speed?
Twice the speed.
Twice the speed, right? Okay, so that tells you what the answer should be. So if I have cf of x prime, it will be cf prime of x. That's exactly what it is. If c is equal to 2, so you have doubled your location function on the left, and you ask yourself, how fast or where was I going? Well, you were going twice as the original. So this is the original, and this function is new. So suddenly you are covering twice the distance. The direction does matter, so that's why you double the speed, but you also can say double velocity. If you're moving in the opposite direction, you still multiply by 2. You can multiply by -2 if you are suddenly not if you multiply by -1. That's the interesting example, certainly. If you choose c to be -1, then what happens is you cover the same distances but in the opposite direction, right? And then once again you ask yourself, what has happened to my velocity? It becomes the opposite once again. So the speed is the same, by the way. The speed is the absolute value of the velocity. But if you were talking about velocity has reversed. So this was the original, and this is new. The same. You're going as fast, but in the opposite direction. Okay. So then the rule is, the constant multiple rule is the derivative of the multiple is the multiple of the derivative and once again you have to have a caveat: the function is differentiable. Okay, so as an example, Once again, it's really not that complicated. So once again, these rules are fairly simple. You will become comfortable very quickly if you just do it a few times, especially if you have already enough of the experience with the limits. So in fact, this is the simplest example probably. 3x squared, and if we need to know its derivative, we realize that what's inside is a multiple of the familiar function. So that's the key of the kind of your strategy is to you're facing a new function, you got to find a function that is familiar. So this is familiar. Familiar in what sense? In the sense that we know its derivative. So we know derivative of x squared, so that's all there is. I can apply the constant multiple rule. Once again, I put it like this above the equal sign as a comment to justify the transition. So it will be 3, the derivative of x squared prime. Okay, so, and then as you can see, I have simplified. So that complexity that was inside of the differentiation sign, that prime, now it's outside. So I'm not worried about it anymore, and I just deal with the function that is familiar. So derivative is once again 2x, and I'm done. The answer is 6x. Sometimes that's all that it takes, and sometimes there's more because there are more algebraic operations, and so there are 2 more at least. Well, there are actually 3 more. The two algebraic operations that are left are multiplication and division, and they all have separate rules. And there is the third rule that is that's composition. Okay, the third operation on functions that does not have a corresponding operation on numbers, and that's the composition. But rule is not really that complicated. So what's missing right now is we need more functions. Right now, the 2 rules are only useful when you recognize familiar functions in those expressions. So we recognize x squared, but we don't have anything else. We have just too few functions in order to use for our rules. So what we're going to do next is we need more derivatives, and some of the derivatives will have to be computed from scratch, unfortunately. So this is fairly easy, but functions such as exponential function, logarithm, and trig functions, sine, cosine, these have to be computed from scratch, from the definition. So we'll do that next time. Okay.